Okay, and we're recording. So last time we were talking about confusion of variables. Remember, the big idea is that when you have a composition of two functions, for example, right, you want to make sure that it's clear what your variables mean, right? And so in particular, the thing that comes out of the first function, if you're composing them, that's supposed to be the thing that goes in to the second function, right? Which unavoidably means that if your first function f is thought of as a function of x, then your second function can't be thought of as a function of x. It must be thought of as a function of something different, right? And so if you find yourself with a question that's been phrased forgivably but awkwardly, right? Like, here's two perfectly good functions. There's really nothing wrong with writing two functions like this. It's when I decide that I want to compose them that kind of the problem comes up, right? But strong case could be made. This is not the question asker's problem. This is the question answerer's problem, right? So that being the case, when this happens, all you have to do is just decide that the function that came to you, written with x as the dummy variable, you should rewrite using a different dummy variable. Sidesteps the problem completely. All the risks that come about with, for example, this tempting but wrong solution, all those risks just disappear. All of the confusions of, wait a minute, do I plug in x here? Oh, wait, no, in this place, x is actually f of x. That kind of nonsense. It's super confusing because it's kind of contradictory. It really is, right? I mean, that's literally, there is a confusion of variables problem. All that goes away. Right? All you have to do is just make sure to set up the question in a reasonable way, and as we must do here, rewrite the second function in terms of a different dummy variable. Just so, something to keep in mind. Now, we went through an example of this last time, so I won't repeat the example, but same story, multiple variables. Really morally the same. And now I want to point out that this is really a special case of a larger problem. So let me just remind you, when we first wrote down the chain rule, we wrote it down in relation to composing two multivariable functions. Fine. We then created a corresponding diagram, such as stuff like this, and this diagram proved useful in terms of, you can kind of think about how changes propagate, and that's nice and everything. But let's not lose sight of the fact that our chain rule that we understand at this point only applies to compositions of functions. You can't just write down whatever diagram, directed graph connecting variables to other variables and then just assume that you can just write down a chain rule. We don't have that. All we have is a chain rule for literally compositions of functions. So this is an awkward scenario. I mean, how would we deal with this situation? And I point out there's some real nasty problems involved here. For example, what in the world does this right here, partial of z1 with respect to x1, what does that even mean? And let me just choose a better color for one thing, right? But partial of z1 with respect to x1. Okay, well, z1, here it is. It's a function of, oh gosh, what's it a function of? You see the problem already, probably. I guess I could say that, look, these are the variables that kind of feed into it. So maybe, as in this example down here, let's see, we'll get to this example in a minute. Z1 is to be thought of as a function of x1, y1, and y2. That's okay. There's nothing implausible about that. You could imagine that there could be an example, we're going to see one momentarily, where in fact, yes, the equations that relate the various variables include among them something like this, right? And in fact, this diagram that I'm complaining about is literally what you would write down immediately from the statement of this question, right? So this kind of thing can come up, and yet, what on earth am I supposed to take from this expression? Partial of z1 with respect to x1. That would suggest that I'm supposed to have x1 be my variable, and that then y1 and y2 should be held constant. Wait, I can't. Right? If, let's see here, if I can, oh, come on, zoom. I have to get this far enough away. There we go. If I change the values of x1, if I, literally, in taking this partial derivative, I entertain, okay, I'm going to be changing the values of x1. Well, y1 depends on x1. If you change x1, you're going to be changing y1 too. You can't hold it constant. Right? So I don't even know what this means. Everybody see the nasty problem that comes about here, right? So the only way that we have around this right now is what I have over here, and that is to recall that the only chain rule we know, let me get back into color mode here, concerns exclusively compositions of functions. And when you compose functions, I mean, look, you'd really better make sure you haven't confused your variables, right? You need to have different names for all the variables and all the different roles. That's problem number one. We've already seen what can go catastrophically wrong if you don't do that. You need to make sure that your inputs are all independent. So, for example, if I look at this function f right here, right, the inputs, the inputs for this function f, x1 and x2, yeah, right, they're independent. Changing x1 does not necessarily change x2. Right, they're free to do whatever they want. And then furthermore, lastly, if I look at the composition, the color's getting out of hand here. Let me clean up my mess here. What comes out of the first function has to be what goes in to the second function. Right? So, so the inputs for the second function, the outputs from the first function, those have to be the same. That's what it means to compose. Right? So make sure that your diagram fits in this form, and if it doesn't, you can't use that diagram as written, at least not with the way we have things set up here. So let's get to this example down here. And again, here's the statement of the question. And you see I have various variables or functions of various other variables. Y1 is a function of x1 and x2. Okay, so that's represented in our little diagram that we're generating. And you can go through this list of equations. You will generate this diagram. And as previously noted, this is a problem, right? This is, I don't even know what that, where is the composition of functions here? Which are the intermediate variables? Are these other requirements up here satisfied? No. This is bad. This is just not of that form. Right? So we don't have a chain rule that applies to this scenario. Now here's the fix. And I don't want to, don't think in terms of finding a magic solution that will always work no matter what equations, no matter what directed graph you write down. Look, there's a lot of directed graphs. This can get real nasty, real weird, and I can't address every scenario, right? And you're not responsible for every scenario. But sometimes there's a really easy little solution, such as what I've done here. You'll notice that I basically just introduced a new variable. Let's see here. Kind of right there, that I'm calling x1 star, which is just x1, right? It's just x1. I didn't really do anything. But I can now say I'm going to think of z1 as being a function, in the sense that z1 was a function of x1. Well, now I'm going to think of it as being a function of x1 star, which is x1, so I didn't do anything. Perfectly fine. Right? But it allows me then to change what my diagram looks like. I no longer have to deal with that diagram now. oh, come on. Okay, now I can deal with this diagram, and it's all good, right? This function, what goes in, what comes out of the first one is the same as what goes in to the second one. It's literally a composition of functions. There's no confusion of variables. There's no lack of clarity as to what a partial derivative means. Right? So one little tiny little itty-bitty little tweak. And then if you want to compute, for example, as we do in this example here, if you want to compute the partial of z1 with respect to x1, all right, there's z1, there's x1. There's 3 intermediate variables and therefore 3 paths. There's the what you might call the x1 star path, and thus the x1 star term. There's the y1 path and term. There's the y2 path and term. And the chain rule proceeds. There's really no tricky curves at this point. In fact, if anything, there's a little bit of good news that you'll notice that we find ourselves here looking for, I forgot what color I used, but the partial of x1 star with respect to x. Oh, cool. That's easy. That's just 1. So that just kind of disappears from the equation. Everybody kind of on board with the general strategy here? All right, so neat trick, heads up. All right, moving along. Okay, so second derivatives with the chain rule. Again, not really that deep of an observation, but if you have a function of x and y, when you take its partials, still they are functions of x and y, so you can talk about their partials, right? Same idea that we saw from higher order partials when we first talked about them. So now let's see, how does that affect our use of the chain rule? I'm going to start with I'm going to basically just do an example. I think you'll see kind of I think it's more important to understand the gist of this, kind of get the hang of it, as opposed to rigorous, formalizing of what we're doing. I don't think it pays off. So here's the idea. Suppose we're given some nice function where z is a function of x and y, so entered on my diagram. And then suppose I also think about the polar coordinates r and theta. Now let's remember what that means. Polar coordinates means that x and y are functions of r and theta. Right? And that's how we choose to look at them anyway. So all of a sudden you see I have a composition of functions, and now with this composition of functions noted, we ask the question, let's compute the second partial of z with respect to r. And you see that now you can see the problem. We're trying to take a second derivative through a composition. We're kind of hoping to use a second derivative chain rule or something here. Right? So let's see how this plays out. Okay, so first let's talk about just the plain old first partial. This is straight up. There's nothing weird here. X, intermediate variable, x, term. Let's see here, y, intermediate variable, y, term. Nothing happened exciting there. I guess I do get to capitalize on the fact that I know polar coordinates, right? So because we're using our usual polar coordinates, y is just r sine theta. So the partial with respect to r is just sine theta, right? That's old news. That's just a partial derivative. Likewise, there. And then also, no big deal, but I'm going to use this notational alternative, and you'll see why in just a moment. This notational alternative for the y partial, and this for the x partial. And again, you'll see why in a second. Okay, everybody on board so far? Haven't really gotten to the second derivative yet, but set up. Okay. Now, to compute the second derivative we're interested in, I'm going to take this first derivative, right? And I'm going to take an r partial of that r partial. Again, didn't really do anything yet. Just, a second partial is r partial of r partial, and we've already computed that first r partial. And now, here's where we have to start being careful. I've got to make sense out of where is this on my diagram, and how do I deal with the fact that I have a product of two things here. This isn't just a single variable, so what's going on? And roughly speaking, the way we deal with this is just make this one recognition that we started with here, and that is, if you have a function of x and y, then its partials are also functions of x and y. Let's just recognize that on our diagram. So just to keep this on the screen while we're doing this, if z is a function of x and y, which it is in this situation, then zx and zy are also functions of x and y. And I'm just literally going to add them onto the diagram. I'm going to treat zx like it's a variable. I mean, I could give it a name. I could call it w if it, make you feel better. It doesn't. There's no need particularly. I think it's better to just leave it as zx. Certainly, I think we can agree though that it's easier to think of it as the variable as zx as opposed to writing it with this fraction Leibniz notation. Right. That's why I wanted to rewrite it with a subscript. It looks a little bit more like a variable, but just treat it like a variable. That's all there is to it. Everything else is just follow the rules of the chain rule. So let's proceed through that and see how that plays out. Back to zooming in. There we go. How are we going to take the r partial of zx cosine theta? Now, the first thing I'm going to do is I'm going to make the observation that cosine theta is a constant for these purposes. Now, how did I know that? What was the giveaway that for this part of the calculation, cosine theta is a constant? Well, let's keep track of what we have. Zx is there. Apparently, I'm taking a partial with respect to r, which is there, which means, partial derivative means that the other input variable is constant. So theta is constant, and that means that cosine theta is constant. Everybody on board? Notice how handy the diagram is. It's answering so many questions for us. Not only telling us where are the paths that are going to contribute to the terms that we're going to need, but which variables are playing what roles. I mean, a lot of students, without using a diagram, would get confused and think that there must be why isn't there a theta term in the chain rule? And they're confused and thinking that theta is an intermediate variable too, which it isn't. You can see right over there. Theta is one of the initial inputs. Okay, so theta being a constant, cosine theta being a constant, I can factor that out and reduce the question now down to what is the partial of zx with respect to r? Whoops, I'm going to need the... Let's do it like this. There we go. So zx, r, theta is a constant, so cosine theta is a constant, so nothing happens with that. But how do I take the partial of zx with respect to r? Okay, well, diagram. Let the diagram be your guide. There is an x term, and there is a y term. And I'm just writing down the chain rule as dictated by the diagram. Anybody all right? Yep.
Why did you add the CX, CY instead of using just the C?
The what now?
The CX and CY.
ZX and ZY?
Yeah.
So keep in mind what I'm actually interested in is what my colors are getting out of hand here. Let me clean up. I'm actually interested in the second partial, which means the r partial of the r partial that I computed initially. Right? Is that cool? Right? And so unavoidably, as part of computing this, I need to take the partial of zx with respect to r, just as part of that. That's just kind of how the cookie crumbles in this case. Does that make sense? Yeah. Okay. All right. Okay, so let's see here. Chain rule problem, terms from the intermediate variables. And now, okay, likewise, very analogously, what do I do with the partial of zy with respect to r? Well, again, I have clearly two intermediate variables, and thus two terms, and thus this. And of course, just like in the previous, sine theta is a constant, so it just comes along for the ride. Everybody all right? That's all over but the shouting at this point. Now we just need to kind of, write down a few things. Let's see here. Does this all fit? Yeah, okay, cool. So partial of zx with respect to x is just zxx. There's no composition in there. Z is directly and immediately a function of, among other things, x. So that's just a rewrite. Again, I know polar coordinates. So a lot of this is just immediate from polar coordinates. Again, constants that come along for the ride. It didn't really do anything there. Again, notational, nothing really happened there. This is all just kind of rewriting a couple of things. And then with all of that having been done, you can kind of multiply, combine things together, and here's your final answer. So if you want to compute... there we go. Okay, so if you want to compute a second partial with respect to r, but if your function's not written in terms of polar coordinates, if your function is written in terms of x and y coordinates, it might be easier to deal with than x and y coordinates, depending, right? Then this is the formula for how you can compute the, potentially physically natural second r partial that you need without having to venture into actually rewriting everything in polar coordinates. And this becomes a plug and chug. Okay, now let me try to persuade you that this is actually good for something. I know y'all are largely engineers, and so how is this going to make your life easy? How is this going to help you build a better widget, right? So here is an object of great interest in physics and surprisingly other areas, even economics. In finance, this comes up. It's weird, kind of unexpected. But anyway, object of great interest. This is called the Laplacian operator. This is unavoidably critical to understanding how heat flows. Right? If you have a hot spot in the room over there, the heat will kind of flow through the room. Well, how does it do that? And what points get how warm, how fast? Right? It's a very difficult problem. Right? To understand that, you need to understand this thing called the Laplacian. Likewise, how waves move, how electrons behave. If you want to solve the Schrödinger equation, this Laplacian is very unavoidably important there. So it's really a very physically natural thing. And notice I've got it written in terms of rectangular coordinates because x, y, and z. All right, what if I wanted to do this in terms of spherical coordinates? And I'm going to claim, without the algebra, that this is what it's equal to in spherical coordinates. Notice down here, all of my partials are with respect to like theta and phi and rho. It's all partials with respect to and factors in terms of spherical coordinates. Now, how did I get from here to there, you ask? Well, roughly speaking, we're going to go that way. We're going to go up, not down. This turns out to be easier. In particular, let's start and think about what is the second partial of f with respect to theta. And check it out, we're back to this page. We're back to trying to understand partials, higher order partials, in terms of new coordinates like r and theta. I did polar here. It's spherical on the next page, right? But second partials with respect to non-rectangular coordinates. That's what this does, right? So we see how to take second partials with respect to non-rectangular coordinates. Well, just do that, and you can write this in terms of rectangular coordinates, and you can write this in, I wanted a different color there. You can write this in terms of rectangular coordinates, etc., and you can go through this whole thing. I'm not suggesting that you do this, mind you. It's very tedious. If you really want to work out, right, chain rule, heavy algebra, multivariable workout, then okay, I guess you could. It's very tedious. But if you do, write down all these terms. Here's your diagram, right? Rectangular coordinates are functions of spherical coordinates. Then you will find that this is equal to that. Okay, who cares? What does this help me? How does this help me, again, build a better widget? How does this help me compute stuff? Here is a very natural, very real-world situation. And that is, for example, suppose we want to understand what it means to be a solution to this equation. This is called the Laplacian equation. Again, this is very, very important in a lot of physics and engineering. Ultimately, this is what describes how electrons behave and how mass behaves in a gravitational field and stuff like that, which the details of which are going to come from your engineering and physics classes. Right? But the Laplacian, how do we solve the Laplacian, or more to the point here, how do we confirm if we have a solution to the Laplacian? Well, keep in mind our Laplacian, which we originally wrote down like that, we've rewritten in spherical coordinates like that. Let's see here. This candidate function, f, that in spherical coordinates I would write like that. In rectangular coordinates, that would look like this. And by the way, why am I interested? Where did this function come from? It just turns out this is going to be the right answer. So let's think about what's going to end up being the right answer. Right? And so again, that f, I can write it in rectangular coordinates, or I can write it in spherical coordinates. So if you want to check this equation, your options are to compute either this expression or this expression. And I am very well aware that this might not have made a sale for you, right? You might be thinking, you know what, thanks but no thanks with all this spherical stuff. I think I'll stick with this one's half as much and no funny Greek letters, right? I get the appeal. That's actually not going to pay out the way you think. This calculation up here is hard. It is tedious. You are going to have to do it at some point in this class because it's one of the book exercises, and it is a really important calculation. Everyone should do that once in their lives. Your time's coming soon, right? So but you'll see how hard this is going to end up being. But let me walk you through this calculation right here, and it turns out it's easy, so easy, nothing to it. We can do this almost entirely in our heads. There you go. Let's start with looking at this term right here. Very first thing apparently I need to do is to take a theta partial of this expression that doesn't have any thetas in it. 0. This whole term just disappeared in a puff of smoke. Right? That's awesome. Okay, next term. Let's look at, I'll look at all of that ugliness applied to this function. And again, the first thing I have to do is take a phi partial of this expression that has no phis in it. So again, disappears in a puff of smoke. I like this, right? You should like this is good news for you. If you're doing one of these Laplacian calculations, most of this just disappears. Totally awesome. And then lastly, now we actually have to do a little bit of actual work here. If I want to apply this operator, that term in the operator to this expression. Okay, well, fine. You know what? I do have here a row partial of 1 over rho, k over rho, and so there's going to be a 1 over rho squared, and constant, whatever. So that's going to be 1 over rho squared, which, when I multiply by rho squared, makes this a constant, and when I take the derivative then of a constant, as you can see here, derivative of a constant, again 0, and that all goes away, and we have now conveniently, basically effortlessly confirmed that this function satisfies our Laplacian equation, right? We computed that this was 0, so therefore we have a solution, and therefore we understand immediately, just from a couple of quick, easy observations, we have a significant understanding now of how gravitational potential works, how electric potential works. It's pretty awesome. Right? And again, the thing that makes this all possible in the first place, there it is. The thing that makes it all possible in the first place was this reformulation of the Laplacian, which was made possible by second derivatives in the chain rule, like we did on the previous page. Everybody all right? So I hope you're persuaded that this is actually really important. By the way, this is one of the topics that's not in the book, as I recall. At least I didn't see it in the book. So this is one of the topics that's enumerated on the content syllabus in the included material column. Right? So it's not in the book. I think it's an unfortunate oversight, in my opinion. And so even though it's not in the book, it is fair game material for this course. Okay. Moving along. So section 2.6. Let me start with a quick review of some stuff that you already know. This is just kind of summarizing what we know about partial derivatives, right? So partial derivatives, whichever direction, whichever of these several variable axes represents the direction you're going. Well, we know that it's the slope of the graph in that direction. We know it's a multiplicative factor as you move in that direction. And I claim we know a few other things about it. These formulas that follow we haven't actually written down yet. This one over here is actually kind of a freebie. If you think about the formula here, this expression, gradient dot standard basis vector, well, the gradient, by definition, has elements that are partial derivatives. And when you dot with a vector whose coordinates are almost entirely 0 within a single 1, you will get the corresponding partial derivative. You can just literally dot this out. It's mostly zeros. Dot this all out, you get that. So it kind of I'm going to say we kind of knew that. We hadn't written it down. It seemed pointless to write it down, but we kind of knew that. And then this other one, I claim that we know that a partial derivative can be written like this. This is a rewrite that seems a little unnatural. It's basically just taking the computation of a partial derivative and writing it as a derivative of a parameterization. Remember, when you're going in the xi direction, that's what a partial derivative means. It means that my inputs are moving exactly and only in the xi direction. Notice that that's all this thing here on the inside does. A plus TEI has me at the point A when t is 0. And then as t increases, I am moving in the EI direction, namely in the XI direction. So these are morally kind of this. They're saying the same thing. Both of these expressions say, hey, how fast is F changing as I'm moving in the ith axis direction? All right, so that's just kind of a quick review, and now here's the pitch I'm going to make. This is going to seem a little strange. How to start this? I'll remind you that partial derivatives are thought of in terms of coordinates, And the pitch that I want to push onto you here is that coordinates are kind of arbitrary and made up. Kind of made up. It's not real. Coordinates are, I mean, again, we pulled them out of thin air. There's nothing saying that you have to set up coordinates at all. And if you do, how you set up those coordinates is totally your imagination, your decision. It doesn't really ultimately matter. So, for example, let's talk about in this room. And as y'all recall, one of my favorite metaphors for a multivariable function is temperature thought of in terms of position, right? So it's really warm up there next to the projector bulb. It's probably very cool over there in that far right bottom corner because it's in the shade and there's no people next to it. Close to the door, it's probably a little tiny breeze from under the door. So temperature is a function in this room. Now I can talk about the temperature at this point right here without making up coordinates. Right? Temperature as a function of location, it's literally a function defined at points. And whether I choose to call this XYZ or PQR or how I set up my axes, that's up to me. It's not really intrinsic to the situation. Is that cool? Right? I mean, coordinates are arbitrary. Right? So, okay. If I, as usual, set that as my X direction and that as my Y direction and that as my Z, straight parallel to the walls and straight up and down, etc. If I set that up, then I know various different things about the partial derivatives. Okay, here they are. Partial derivatives are all of these things. So in particular, then, all of these things are equal to each other. And I know that about this direction. Why? What is it about this direction? It's because it's in the direction of one of the axes, which I pulled out of thin air. There's no mathematical reason I have to set up my axis pointing that way. Right? Instead of using these as my axes, perfectly fine to use these as your axes. There's nothing physically wrong with this. It's just as good as that. So now let's suppose momentarily that I were to set things up like this. So forget about the walls and the corners and straight up, etc. These are my axes, right? Okay, well, if those are my axes, then that direction is now in the direction of an axis. This is a standard basis vector direction, and therefore all of these things are equal, not just for that direction, but also for that direction, or that way, or that way, or that way. Take your pick. Any direction you want to go could be an axis if you just set up your coordinates that way. Is that cool? So, we would write these things differently depending on the coordinate system, but what remains is that these expressions all equal to each other, no matter which direction you're pointing. So the big idea then is to just, I know that apparently this expression, which is that expression, which is the slope of the graph, which is the multiplicative factor, these things are all equal to each other. I know that because I could have set up axes in those directions, but I didn't, and I don't want to, and I just want to use this fact in my regular old, plain old, familiar, convenient axis system that I'm already working in, and so I just have to come up with a different name. I can't call this a partial derivative because it's not actually in the direction of an axis, so I'm going to give it a different name. We call this a directional derivative. And when you see this term, directional derivative, what I want y'all to think is, okay, it's morally a partial derivative. This is the exact same thing as a partial derivative. I'm just not going in the direction of an axis. It could have been in the direction of an axis. It just didn't. So that's the big idea. So now there's different ways to write this down and draw these conclusions. I think this is ultimately the best one. One thing you're going to notice in this class is that I'm going to be trying where I can to pull y'all away from the comfort of thinking in terms of coordinates. Because look, don't get me wrong, coordinates are great. For computations, yeah, you got to use coordinates. Oh my God, super handy, right? Computationally, no doubt. But it's a choice, and it's not really intrinsic to the problem, and it can be very confining. So that point of view, I think that's the value of this point of view. It helps me hopefully persuade you of how limiting it is to pick a coordinate system and stick with it and not recognize the validity of any other coordinate system. That's just naive. Okay. All right. So, a bunch of free information. I can define this thing called a directional derivative by this formula. You can see right here that this asserts this addresses the question of what happens when I move in the direction of some unit vector, presumably not a standard basis for any unit vector, and I'm moving in that direction. I want to know how the function's changing. And I have, as an immediate consequence of the arguments we just made, I have a handy-dandy formula for how to compute it, and I have two really valuable interpretations of what it looks like and how it connects to geometry or physics. All right. Now we're going to do a couple of examples on the next page, but before we do, I want to introduce one little bit of notation. So looking at this interpretation right here, that this is a multiplicative factor. It's what I multiply by ds to get df, or feel free to make those velocities, take your pick, right? I claim, if you think about it, with this getting multiplied by a factor to give this, right? Now this is just a kind of a rewrite of what I wrote in English here. I'm just writing it in algebra here. The thing that you multiply by ds to get df, the thing that you multiply by ds dt to get df dt, doesn't it make sense that thing should be called df ds? It just makes the algebra look good on the page. Right? It's a perfectly reasonable choice and very handy, very intuitively satisfying choice. So this is the last little thing I'm going to say before our examples. Alternative notation for a directional derivative is to write it as df ds. Not df dt, but df ds. Rate of change with respect to distance that you move in whatever direction you're going. Okay. All right, so let's do one. Okay, we're good on time. So, here is a question. You'll notice we have a function given, and we're interested in the slope of the graph. How would I compute the slope of the graph? And had the question been to find the slope of the graph in the direction of one of the axes, then I would have just said, partial derivative. That's exactly what a partial derivative is. But it's not, right? This wants to know the slope of the graph as I'm moving in the direction of this other vector. So a partial derivative is not going to do it. But so this is the perfect situation to bring up directional derivatives. Again, a directional derivative is morally, think partial derivative, but in a non-axis direction. Exactly what we have here, right? I want what would have normally been computed with a partial derivative, but I want it in a different direction, and so the answer is a directional derivative. Everybody okay? All right, now here's the sticky trick situation. You notice it says here the direction of the vector 3, 4. A lot of students would then say, okay, then 3, 4 is a vector that I want to use for my directional derivative. Sure seems like it should be. But recall, this has to be a unit vector. If you pick a non-unit vector, then you could still make a case about arbitrariness of bases, but you'd be fundamentally changing the geometry of the domain that you're working in. And that you just really, okay, it's not that you can't do that, but it would give you something that doesn't mean what you would hope it would mean. I'm going to skip the details on that, but I claim if you restrict yourself to a unit vector, then everything's good. No nasty, unexpected problems. Okay, so that's the problem here. This vector is not a unit vector. Well, correction. This vector is not a unit vector. Let's talk about the semantics real quick. Notice I didn't say the vector v. I said the direction of the vector v. In B, the word direction is routinely and very conveniently understood to mean unit vector. So when you see something like this, the direction of the vector v, what this means is the unit vector that points in the direction of the vector v. And of course, how to find a unit vector that points in a given direction, you just take the given vector and you divide it by its own magnitude. This is old news, right? This is from the first day of class, second day of class, something like that. So v over 5 is our actual unit vector. And then it's all over. But the shouting, we agreed we wanted to compute slope of the graph and that is a directional derivative. Don't forget we have this handy formula for computing directional derivatives. So yeah, compute your gradient, dot it with your unit vector, multiply out the arithmetic. That's all details. Works out to be this. Everybody all right? Okay. Real quick. You do have to be very careful with the language. When I say in the direction of a vector, keep in mind what a vector is. A vector is, most fundamentally, a direction and a magnitude. Again, don't think about coordinates, and I specifically don't think about this as a point. This is a vector. This represents a direction and a magnitude. Where 3, 4 doesn't have any bearing on this problem. There is a point, 3, 4. That's not what we're talking about here. So here's the nasty landmine that some students will step on, and that is to say, okay, well, I find myself at the point 3, 1. There's 3, 1, and let's see here. 3, 4 is my vector, and that's what I should be thinking of. That's the vector. Here's the unit version of that vector. But if you mistakenly view this as being a point, and if you mistakenly interpret this as I'm at 3, 1 and moving toward the point 3, 4. Well, the point 3, 4 is about like that. No, it's not that high. Let's see here. The point 3, 4 is about like that, which would have the student thinking that you're going in that direction, which you're not. Right? So heads up with the language. Again, the direction of the vector v is not the same as toward the point whose position vector is v. Totally different. Make sure to interpret carefully and correctly. Okay, now let's see. How am I doing on time? We have 1 minute. Okay, let me, you know what, I'm going to, well, oh gosh. I don't think we can quite get to this next example, so I'm sure I owe you a couple of minutes anyway, so we'll draw the line right there for today, and see y'all on Wednesday. Okay, have a good one. See ya.